Okay, I meet you again in our video on Introduction to Engineering Design. Okay, my name is Satrio Wicaksono. For today, I will explain you about conversion from chemical to thermal energy. Okay, as usual, before we start our class, we always started with the expected outcomes of the week. Okay, our expected outcomes today is students able to understand the principle behind fuel to energy conversion. Okay, if you look at the slide, you can see the conversion from our fuel to kinetic energy is like this inside of our car. You can see at the beginning we have 100%, but because of engine efficiency, only around 18% that is converted to kinetic energy. And after that, there are several losses like driveline losses, and we only get like around 12% into the wheel. After that, we still have some losses. Aerodynamic drag around 2.6%. Besides that, rolling resistance as well is around 4.2%. That's why actually there are a lot of losses in our car. Okay, inside of our engine, as I explained last week, okay, there is a combustion. Combustion, what is combustion? Combustion is actually oxidation of a fuel to generate heat, and it will create light as well actually. Okay, and oxidation itself is chemical reaction of a substance with oxygen. Okay, and in our engine, what happens is we will have fuel and we will have oxygen as well, and because of the reaction between those two, okay, it will create heat. Okay, and this is the stoichiometric equation of ideal oxidation. I believe you have already studied it in high school about in chemical, okay, in high school. Besides that, you studied it in your chemical subject as well in ITP. So I believe you already know how to solve this. Okay, if you do it correctly, you will get the coefficient A is 32 and B is 44 and C is 18. Please try at home. Okay, so later inside of the class, we won't discuss it for too long. Now, because of that reaction, there are some heating values happening there. Okay, in the left hand side, from the C2H8, if I'm not mistaken, okay, we will have around minus 5771, okay, kilojoule per kilogram. And after that, from oxygen, we have none. And on the right hand side, from CO2, we will have around minus 17,106. And from the water, we will have around 15,759. Okay, so total we will have 27,100 kilojoule per kilogram. Okay, and this is some comparison on heating values of other fuels. Okay, there are a lot of it. Okay, there are methane there. It's quite high. It's very high actually, 55,650. Benzene. For some non-hydrocarbon fuel as well, we will have it here. The thing is, before you go inside of the class, please study about what is heating values. What's the purpose of heating values? Okay, what it tells about. So later in the class, we will have more involving discussion. Okay, the thing that I told you about before is ideal combustion. But actually in our world, air, okay, air is not consists of 100% oxygen, but it's mixture between oxygen and nitrogen. Actually, it's mixture between a lot of things, but the main component is not nitrogen and oxygen. Nitrogen is around 79%, oxygen is around 20%, and the rest we have a lot of other components, but not that much. Okay, that's why for the normal combustion, this is the stoichiometric equation. Okay, you can see there that previously we only consider the oxygen, but now we consider the oxygen and nitrogen as well. Okay, and as usual, please try to solve this. Okay, inside of the class, I will ask you directly the value of D there. Okay, the value of D for nitrogen. For nitrogen there. So please try to do it and let me know inside of class. Okay, and next I will teach you about the trends in hydrogen and carbon ratio. At first, in 19th century, we know about coal, and the hydrogen and carbon ratio is 1:1. Okay, and after that, in 20th century, we have diesel, we have petroleum, we have natural gas. For petroleum is 2.25 to 1. For diesel is 2.125 to 1. The highest here is natural gas. It's 4:1. Okay. Now in 21st century, we are expecting of fuel cell. It's infinity to 1. So it's very huge. Okay. Okay, try to do it as well. Previously, I tell you about the oxidation of petroleum. Now, try to solve this as well. How it can happen, how we can get these values. Okay, the oxidation of diesel. Okay, now I will tell you about hydrocarbon. Okay, hydrocarbon, we normally found it in crude oil. It's actually combination between hydrocarbon itself, sulfur, and nitrogen. Okay, how to get that? Okay, before I explain further about it, you have to know that hydrocarbon has different different chain length. Okay, because of this chain length are different, the weight as well is different. That's why if you found hydrocarbon that have from C1 to C4, okay, is in the shape of gas. Okay, C5 onwards, it's liquid. Okay, and if we find long C, it's solid. Because of the difference in structure, we will get a difference in boiling points as well. And because of this, okay, we can separate hydrocarbons by distillation. Okay, and this is the process. If you look at it, okay, if you look at the slide, this is the distillation process. At the beginning, at the bottom, the temperature is very high. Okay, the temperature is very high, and you can see that actually at very high temperature we can get lubricating oil, paraffin wax, and asphalt. And after that, going upwards, the temperature is getting lower. At 370 degrees C, we can get fuel oil. Okay. At 300 degrees C, we will get diesel oil, 200 degrees C, kerosene, 150 degrees C, gasoline, and gas for around to 20 degrees C. Okay. If you look at it, it's actually based on, as what I told you before, it's based on the boiling point. Okay, at the beginning, all of the hydrocarbons are boiled, and for example, at 400 degrees C, only lubricating oil, paraffin wax, and asphalt that is in the liquid mode. So we can extract those. When the temperature is lower, for example at 200 degrees C, kerosene is at its liquid shape, so we can extract that. That's actually the way we extract hydrocarbons using distillation process. Now, the same as last week, okay? Our purpose right now is to replace the non-renewable energy source to renewable energy source. One of it is biofuel. What is biofuel? Biofuel is a fuel that is produced through contemporary biological process. Okay. Biofuel can be divided into two: plants, okay, and from agricultural, domestic, and industrial waste. Okay. This is the process of biofuel. Please read about it. Okay. It's showing you the process from we are harvesting biomass, and after that processing in order to get biofuels. Okay. The other biofuel, there are several biofuel. The first one is bioethanol. It's an alcohol made by fermentation, mostly from carbohydrates. Okay. Produced in sugar or stretch crops. The plantation is, for example, corn, sugarcane, or sorghum. Okay. Things about ethanol is actually can be used for fuel in its pure form, but most of the time we use it as gasoline additive. Besides bioethanol, we have biodiesel. Okay, the same as bioethanol. We can use it in pure form, but most of the time we use it as additive. You can see in the slide that biodiesel is actually produced from oils and fats. Okay. Beside biodiesel, we have green diesel as well. It's slightly different from biodiesels. It's produced through hydrocracking biodiesel oil. Okay. You can see here, this is the difference between green diesel, petrodiesel, and biodiesel. Okay, for petrodiesel, it's 100% from crude oil, and for biodiesel and green diesel, the difference is as you can see in this slide. Okay. Actually, for biodiesel, bioethanol, green diesel, all of those information you can search for it in the internet. So before you go inside of my class, please try to study about it first, and we will discuss it in detail in our class. Okay, that's all for today. See you next time.